Welcome back all of you. Today's lecture is the continuation of last lecture, which is basically prediction of failure conditions from MCCM. In fact, in the last few lectures what we have seen is we have got the concept of strength, we have got the concept of stress path, then we integrated yielding and yield curve with these concepts, and then saw how a soil state from its initial state reaches to the critical state. So, in the process it gets yielded and then it reaches the critical state. So, both the yielding conditions and the failure conditions can be obtained from the given critical state models, in some sense by knowing the critical state parameters which we have defined all the while in the last few lectures, and by knowing the geometry, by substituting the required parameters into the equation of ellipse, which is the yield curve, and corresponding to the failure conditions. So, this much we have seen. Now, today's lecture we will be adding a delta information to what we have already seen, that we will try to integrate how this looks like, the whole of the failure looks like from the stress strain response and the volume change or pore water pressure, depending upon whether it is a drained or undrained test. So, that is what we will be seeing in today's lecture. So, it is about prediction of soil failure from MCCM. So, first let us see prediction of normally consolidated and LOC for CD test. It is more or less the same. Much of these aspects we have covered in the last few lectures. So, it should not be a problem. So, it will be more like a revision cum understanding. So, I think it should be easy for you to consolidate what all you have understood till now with this lecture. Let us start with, because in the critical state model what we will be dealing with will be MCCM, that is the ellipse. So, the equation of the ellipse I am not repeating, this we have already seen. Now, for NC or LOC, because both of them exhibits more or less similar behavior, and we have seen that OCR less than 2 can be considered as LOC, and when it is greater than 2, in our previous lectures we have defined it as 4. So, this is not a very strict definition of OCR. Mostly we will come to know by its response and the type of the soil. So, OCR, what is the actual definition for LOC and HOC, that would differ, and it is not a very strict rule of thumb. So, soil is isotropically consolidated to P dash YA. So, this is Q P dash plot. So, this is the maximum yield point, and that comes from the isotropic consolidation. Soil is now unloaded to P naught dash, that is point O. Why? To create a LOC state. So, this is P naught dash, and the yield curve corresponding to this will be this. So, that is the maximum point is P dash YA. Now, critical state line has been marked, and according to MCCM it passes through the center. So, it is P. Now, we have V ln P dash plot. So, this is the isotropic consolidation point P dash YA. Let us say it is unloaded from P dash YA to generate P naught dash. So, this is point P, and here you can see it is P naught dash. So, it is unloaded to P naught dash. So, this is very essential now to find out, to understand this sequential steps. Now, in our previous lectures these were not very strictly followed. I will tell you one more aspect which we did not follow very strictly, but now things are very clear when we integrate the yield curve along with the stress path. So, now P naught dash is on the unloading curve. As I told, we will try to also integrate Q versus epsilon behavior and volume change, because now it is a CD test. So, it is volume change delta sigma of V, which is cumulative volume change. So, these many details we are going to understand for a typical NC LOC in a CD test. So, now we are ready with the initial point, which is P naught dash. Now, we know from our previous discussion also, P dash y A determines the size of the yield curve, and we have also seen that these are the state parameters based on which size of the yield curve gets determined, this one and Q. Now, P dash y A determines the size of ellipse. So, the major axis is given by P dash y A. Now, this particular state P dash y A is NC and P naught dash is LOC, it is very clear. Now, let us do a drained shearing from O, that is the initial point is fixed, then it is drained shearing. Now, we do not have to explain much, because now we know how ESP would look like in a CD test, which will intersect the elliptical yield curve at B. So, this is the condition, like the ESP meets the initial yield curve at B. So, that B is given. So, it is slightly difficult, because if you try to map it, then the amount of space available is quite less. So, you can see that from P naught dash it should move towards B. ESP from O, that is O, intersects the elliptical yield curve at B, where it yields. Now, you need to note one important thing, from O to B it is elastic behavior, and hence it has to move along this green line, that is the loading unloading line. I will come to this again, because we are going to have a bigger picture of this in the next slide. So, I will just tell that the path in V, L and P dash is denoted by this small red line, which is difficult to see, but it will be clear in the next slide. Now, when you map this to Q epsilon, you can see that up to B it exhibits a linear behavior, because it yields only at point B. So, that is the point. So, OB, this is linear behavior. Same, the volume change also, it will not be much, because it is in the elastic range. Okay, so, the B point has been mapped in all the figures. Now, when it is further sheared from here, since it is NC and LOC, we know that strain hardening happens. So, failure occurs when ESP touches the critical state line at F, that is BF. So, this is the further extension of the path. So, it is very easy, that we have already seen before, and then it completes. So, it fails at F. So, from B to F it moves. Now, what happens? You can see that this is a hardening response after yielding, and hence the volume change also will be more. In fact, you are moving towards this particular point and then it comes down. So, it is no longer on the loading unloading line, and hence the volume change is going to be high. So, from B to F there is significant volume change. Now, the same figure we will see in an enlarged version to understand a few more things, which is very important. Now, stress strain response is curved. Up to B it was elastic, and beyond B it is curved. Beyond B, yield surface expands, and then the previous yield curve is no longer valid. Now, this is very important aspect. The moment the stress path crosses the yield curve, I mean to say the initial yield curve, then the previous yield curve which was there, that is the initial yield curve, now it is no longer valid. What is the significance of this statement? Let us see. So, it is again Q P dash V ln P dash. I have done this critical state line, it is a smaller line, you can see this is mainly done to accommodate a bigger figure. The same figure that we discussed in the last slide, we are just going to repeat it. So, it is again P dash Y, the initial point is P naught dash, critical state line, and this is the effective stress path we have already seen, point B, BF. Now, this is an intermittent yield curve, this green one. Before failure, you can see that this particular yield curve, it is not touching the point of intersection of ESP with critical state line. This we have discussed in our previous lectures, that which yield curve defines the failure one, that yield curve beyond which there is no further expansion of yield curve. So, that yield curve which is passing through the point of intersection of effective stress path with the critical state line, and that is this particular point F. So, this intermittent point is given as C, that is point of intersection of ESP with the green yield curve, which is an intermittent yield curve, and then the final yield curve is given as red one. So, what it means is that once it crosses point B, this yield curve is now no longer valid. It goes with green and then comes to red where it stops. Now, there is no further expansion of yield curve, and this we have already talked with respect to plastic potential and plastic strain vector. P dash Y A, we are just mapping it into V ln P dash, and from here the unloading happens, and then the starting point is P naught dash, and when it is loaded, that is from the point O, I can also write here it is point O. So, from point O we know that up to here it is elastic response up to B. So, then if it is elastic response, it cannot deviate from any, but it has to move along the green line. Why? Because we know that unloading reloading line is an elastic response. So, we can easily take it to be along OB. So, that is what is marked, and this is the same thing we have seen in the previous slide. Now, you imagine a situation where we do not know the concept of yielding and the yield curve is not marked, and that is what we have done in our previous lectures. We did not consider yield curve into picture. When we discussed the first few lectures of critical state, you can see that we have not discussed the yield curve. Now, we have drawn the stress path to failure, we have also marked in V ln P dash. If you remember, from this particular point we would have just drawn a curve like this to failure to critical state line. That is because we have not introduced the concept of yielding. Now, once this particular yield curve comes into picture, things are very clear. That means where exactly, up to where exactly it will follow the unloading reloading curve, and from where it will deviate towards the critical state line. Unless we have the yield curve in picture, we cannot do this, and we have followed a line like this which goes to critical state. You can refer back and see for yourself, and this information is complete only when we draw the yield curve along with the stress path. Okay. So, that is all I just want to add here. Now, consider intermittent yield curve with P dash y equal to P dash y C. Just because this is named as C, the extreme yield point is named as P dash y C. So, that is given here. Now, let us draw a loading unloading line from P dash y C just for our understanding. Now, QR, this particular line QR is the unloading line corresponding to P dash y C. Now, shearing from B to C causes deviation from reloading line due to shearing and also by following the concept of yield curve. Now, further shearing at point B, now it will deviate from elasticity and it will undergo hardening behavior. Now, from B it will deviate from point B. Initially it was along the unloading reloading line, which is the elastic response, but shearing at B it has to deviate. So, at this particular point B only it is deviating. Initially we have drawn it as a curve, now it is coming along the unloading curve and then it is coming towards the critical state line. So, this particular point from where it will deviate, it comes from the concept of yield curve. So, point C, let us say that that particular point is there on the unloading line QR, because it is touching here. Now, we are redefining the elastic limit. Let us consider that the point is at C. So, this particular point is the point C. Now, the moment it deviates from point B or the moment it passes point B, we are defining a new yield curve. Now, let us say that the stress path has reached up to point C and it is at point C right now. So, that particular point defines a new yield limit and that is what is shown here at the point C, that is QR is the new elastic response for this particular soil corresponding to point C. So, when it deviates it has come to point C, now it is at this particular point. Now, let us say that you are unloading from point C, that is you have sheared. Now, let us consider that you are unloading from point C. So, what will happen? It will follow this particular unloading reloading line, because now it will become more like an elastic behavior if you are unloading from point C. But if you continue to shear, it will fail at F. That is normal response that we know and it is like this. So, you can see here now from the starting point it is following a curve like this, and initially without knowing this point we have done like this. You can see for yourself that how we have drawn the failure line from O to critical state line. Okay. So, on further shearing it fails at F. Now, from C, if it is one dimensionally loaded, it will proceed along RQ. Now, this information is very important. Let us say from C, for assumption, I am not telling, it is already under shearing procedure, but then to understand how this path will follow depending upon the condition of loading that you apply, that is what I mean to say. Now, if from point C, let us say that it is one dimensionally loaded, not sheared. If that is the case, then it will move along this line, because this is the one dimensional unloading reloading curve. So, it instead of moving CF, it will move along this, provided it is one dimensionally loaded. But in this case we are shearing from C, so it will continue and it will fail at F. Shearing can also be done from P dash by A. Now, let us say that we have followed a lightly over consolidated point at O, but one can always load without unloading. You can load from point P dash by A itself. Now, the beauty of this point is that it has already yielded, it is already at its yield limit. So, it is already at yield point. So, elastoplastic shearing occurs from P dash by A. So, if you start loading from here, it will follow the path and it will move to the critical state line. It will go like this and it will fail on the critical state line, because there is no yielding needed. So, whatever we have understood in our previous lectures, it remains same, but here one additional aspect is the information what the yield curve provides to us in terms of predicting the failure. So, that we have to keep in mind. Now, prediction of normally consolidated LOC for CU test. Now, initially it was CD test, now it is CU test. Most of the discussions remain same, only thing is the volume change is replaced by excess pore water pressure generation. And this is again a prominent point. We know there is no volume change, so delta V is equal to 0, and V naught is equal to Vf. So, this is a very important clue for solving the problem. Later lectures, while we try to solve the problem, that V naught equal to Vf assumption is important for solving the problem. So, again it is the same response. The soil is isotropically consolidated to P dash Ya, soil is unloaded to P naught dash, that is point O. Now, that is mapped onto V ln P dash. I do not think we need any further discussion on this. Soil is sheared undrained from point O. ESP is denoted as OBCF. So, till B the response is elastic. Again I will not discuss this because the slope is 3 by 1 minus 3a, a is equal to 1 by 3. So, it takes the path upwards till it yields at point B. That is the point, same point, O and B is in the same line. So, O and B, so here also O and B is a point, same point. Then it fails to critical state line, that is at F. So, it is the curved response and this is an intermittent point C. That intermittent point is marked here. So, from O to F it is a horizontal line. All these things we have already seen before. Yield stresses are determined from the intersection of ESP with the yield surface. Now, you can see that this ESP meets the yield surface at this point. So, one can always substitute the values in the elliptical equation and obtain the value of Qy and P dash y. Similarly, for F also we will get the value of P dash F and Qf, and that mostly you can get the results from the geometry of the figure itself. Now, B, you can see that this is the linear response. Here also in the pore water generation also it is a smaller response because it does not have much of because it is an elastic loading. The pore water pressure generation is also more or less linear. Now, F, from once it yields you can see that there is a non-linearity coming up and there is a sharp increase in the pore water pressure, and that is why there is a drastic reduction and it moves towards F. After yielding, U increases non-linearly. So, you can see here this BF is a kind of non-linear response. Difference between homologous points between ESP and TSP gives U excess. So, if you want to predict excess water pressure, that is also possible because we know in undrained test what is the total stress path. This is the effective stress path and this is the total stress path, it is at an slope of 3. So, any difference between these homologous point means the same point on ESP and TSP, that difference is going to give U excess. So, U excess at yield, U excess at failure, everything can be predicted merely looking at the figure and determining the total and effective stress corresponding to that. For example, if you want to determine what is the U excess at this particular point, that is yield point P dash y, we need to determine P dash y. So, we know P dash y here it is equal to P naught dash. So, this point is known, one can also determine this particular point. So, this difference will give you U excess at yield. So, it is very convenient to predict what is the kind of pore water pressure that gets generated. So, that is what it means. So, based on the MCCM, that is the elliptical yield curve and the effective stress path information jointly will be able to predict the yield point and the failure point. But obviously, for all these we need to know what is the critical state parameters. So, now let us see prediction of HOC for CD test. Soil is isotropically consolidated to P dash Ya and it is unloaded to P naught dash. The same procedure, but then now the unloading is a bit more, so that HOC state gets emerged and OCR is greater than 2. So, that we already know. So, again the repetition of the same. Now, only thing is here it is volume change and we need to consider both compression and expansion because we expect dilation to happen in heavily over-consolidated soil. P dash by A, so this is the yield curve associated with P dash by A, the extreme isotropic consolidation point. The same is marked on VL and P dash. Unloaded, you can see that it is very near to the Q axis or V axis. So, OCR will be definitely greater than 2, critical state line. So, yields at point B. Now, it is a CD test, it is at an inclination of 3. So, it is not meeting and failing here, we have already seen this, it has to yield first. Now, this point B is similar to the peak condition. Now, from O to B it is elastic because it has to yield first. So, here also it has to move along the unloading reloading line. So, this line, green line, it has to move because it is an elastic response. Now, in our previous lecture we have associated this to peak because the maximum point of Q that you can get for OC is the peak point. Now, here we are limiting it by yield. Earlier we have limited this by a peak line. You can refer back and see in our earlier lectures we have done that. Now, here this peak and the yield point is analogous to each other. We are considering this to be more or less same. And what it will look like in Q epsilon, so up to B it should be an elastic response. Now, in the case of MCCM, we are forcing certain conditions here. When it reaches peak, it is yielding. So, that is what it means. So, yield point B is same as what the peak point. So, here this is one imposing, and we do not know like whether the soil is going to behave in that manner, whether the soil is going to yield at the peak point, this is not clear. But according to the explanation of critical state model, specifically MCCM, what we are dealing now, what it states is that the soil will yield at its peak. So, this is a kind of idealization one has to keep in mind, and hence up to peak the response is also linear. This is also an additional condition that gets imposed because we are considering a critical state framework. So, you need to understand that many things gets idealized which may not be same in the real soil behavior. So, from here now another important aspect, like what is the cumulative volume change. Now, up to here if it is yielding, it is more or less the peak behavior is the end of that initial compression. These things we never bothered when we plotted the results in the previous lectures. We have done all these in our previous lectures right from module 2 onwards, but we never bothered how we are plotting it. So, here there are certain clear indications which we need to follow. Now, at this particular maximum point is more or less the end of compression and where it will start dilating. So, Qy is the yield point and Qy is the yield stress, which is same as Q peak. So, this P dash y is the yield mean stress. Returns and fails at critical state line with shrinking yield curve. Shrinking yield curve also we have seen because this is a strain softening behavior. So, it comes and fails at this particular point. So, from here it is dilating, and that is why there is a sudden drop, and that is the point F, the failure point. I am not getting into the details again because we know this, we have discussed this. Now, that is the failure point P dash F. Now, how does it look like in Q epsilon plot? You can see that there is a strain softening. So, this strain softening we have discussed before, but now at what point it will start strain softening, that dilation happens, that is this is adding more meaning to it. So, by defining the yield curve, you can see that we know along this it will move, that is the elastic response, and then it will move upwards or dilates and fails at F. Now, these information becomes quite handy in the presence of yield curve, that is the yield curve supplements these knowledge along with our discussion. So, from here at this particular point B, strain softening means there is a kind of dilation that is happening up to F where it fails. So, yield and failure stresses can be determined from MCCM by substituting at these appropriate points. So, one can also get the failure and the yield stresses. Now, OB is compression and BF is dilation. Now, this becomes quite strict in the MCCM model, resulting in strain softening. Now, according to MCCM, the actual elastoplastic behavior starts at peak. Now, this is defined because it is explained in that manner. In reality, elastoplastic behavior may start even before reaching peak, which is not captured in MCCM. Now, that is what we need to understand. All the time the model may not represent the actual behavior, but it is a fair good approximation by saying that the elastoplastic behavior more or less sets at the peak, because that is where the dilation would have started, that is the yielding would have started. Now, exactly the peak may not be correct, but it will be around that peak. So, that is what I just need to point out, those differences when you try to idealize the shearing behavior of soil using MCCM. Now, for CU test for HOC, so we have defined all the 4 combinations, that is NCLOC, CUCD, HOC, CUCD. So, now we will discuss CU test. Soil is isotropically consolidated to P-YA. Again the same condition, let us skip this, it is the same condition. So, UXS, now instead of cumulative volume change, now we have XS, X is pore water pressure. Same yield curve, everything remains same, loading unloading curve, P naught dash the point O, the initial point, critical state line. Now, yields at B similar to peak condition. Now, only difference is the slope of the curve, that is 3 divided by 1 minus 3a, we know that it is vertical. So, OB P naught dash from O to B is the yielding. So, here B and P naught dash is at the same point. Now, how does it look like in Q epsilon plot and UXS plot? It is positive instead of compression. So, here is a positive pore water pressure, everything remains same, QY is the point and P dash Y. So, P naught dash equal to P dash Y according to this particular plot. Returns and fails at critical state line with shrinking yield curve. This also we have already discussed. So, this is the failure point F. Okay. So, it fails at F and QF and P dash F is the failure stresses, and strain softening behavior in Q epsilon plot, and you can see that it more or less becomes a negative pore water pressure at failure for OC sample, because of the tendency to dilate in a drain test is same as negative pore water pressure at failure in OC. Now, OB represents positive U, here it is positive pore water pressure, and at BF it becomes negative pore water pressure. And this is very clear from the total stress path with an inclination of 3, which is drawn. Yield point, that is, it is on the left side of TSP. So, at this particular point it is positive U, and at failure point here it will be negative U, because it is crossing the TSP and now it is on the right side. So, P dash F is greater than PF. Now, PF corresponding to failure line, this is the point F. We can see that this is the particular point, if you draw it down, that is PF. Now, you can see that P dash F is greater than P F. So, effect of that is all about heavily over consolidated, and the prediction of Q F P dash F, Q I P Y will happen based on the geometry of the figure and by substituting the relevant equations in combination with the yield curve. Okay, so, we will come to that when we solve the problem. So, effect of ESP on failure. So, we just need to understand two important points here. Slope of ESP, like in what manner it is loaded. Slope of ESP means in what manner it is loaded, what is the load combination that we follow. Now, slope of ESP would influence how it will fail, in which manner it is going to fail. So, that is what we want to demonstrate here. So, it is the initial yield curve P dash y A. Let us say that loading is done in such a manner that slope is less than m. Now, what is m? M is the slope of CSL. Now, let us say you consider a point which is slightly over consolidated at O, and the loading is done such that ESP1, here it is ESP1 is with a slope less than m. You can see this. What would happen in this case? ESP1 is not going to intersect critical state line. So, the loading can happen without failing. Probably it is very close to isotropic loading. So, if ESP is progressing with a slope less than m, it is not going to touch the critical state line. In that case, it is not going to fail. The loading is not going to bring about failure. This is a very important information which comes from here. ESP1 will not produce shear failure in soil. Now, let us consider another case. Again, the starting point is same, and ESP2, which corresponds to NC or LOC soil, which is mostly applicable for excavation. So, this is the way in which the ESP2 is progressing. There is a loading such that ESP2 takes this particular slope. Now, this is a typical case of excavation. For ESP2, yielding has to take place first before failure. We have seen that in all our previous discussions, for NC and LOC, it yields first and it fails, but then it was very easy, it never crossed the critical state line. When did it cross the critical state line? First, the effective stress path crosses critical state line, yields and then comes back, means it is a typical HOC behavior. But now our point is LOC. In all our previous discussion, LOC and HOC, it yielded first and then went ahead towards the critical state line. But now, if the loading such as that in excavation, if it is done in such a manner that it follows ESP2, then it will cross the critical state line. As you can see here, it crosses that, goes and yields and then will come back to failure. So, that is what just wanted to highlight here. An LOC can give a behavior close to HOC during shearing, provided the loading combination is in such a manner that it produces an effective stress path similar to ESP2. So, initial point is NC or LOC, but shearing behavior is similar to HOC. Why? Because it crosses critical state, yield and then gets back to failure. Now, that is all related to the prediction, and another aspect that we can predict based on critical state framework, or very specifically MCCM, is the soil stiffness. So, the next discussion is determination of soil stiffness. Soil stiffness is characterized by elastic modulus E dash, shear modulus G and bulk modulus K dash. K dash and E dash is shown to show that this is relevant only for effective stress condition when it comes to soil behavior. We also have EU and KU which comes from the undrained test, but for very specifically the mechanical properties, we will just consider E dash and K dash, and G does not need any prime because it is a shear modulus. Now, all of these are elastic parameters. Now, in the critical state framework, can we use MCCM or critical state framework for predicting the values of these stiffness? So, we need to confine only to the elastic response of the soil. Now, probably you would get a hint here, like we will be referring only to the unloading reloading line, not the ICL, because ICL exhibits elastoplastic behavior. We are concerned only about the elastic stiffness. So, for prediction, we need to now account for the unloading reloading line of critical state framework. Soil stiffness can be determined using critical state model, triaxial testing and isotropic consolidation results. We need, for determining the critical state parameter, isotropic consolidation and or the triaxial test results. Yes, so how to do this? Let us see. So, unloading reloading line represent elastic behavior. Now, I think none of you would be having any doubt related to this, that it is unloading reloading line that represents the elastic behavior. Now, when we talk about stiffness, it is always better that we discuss it in terms of void ratio, because that is what we are used to. But the same, everything remains same, only thing is the axis changes by 1 plus E in the case of V. So, either I discuss in terms of E or in terms of V, the responses are same, but the slope would change. It is lambda and Cc, Cc in E plot, lambda in V plot. So, there is only difference in the slope values, but all the concept remains same. It is V or E versus ln P dash. So, here instead of writing V is equal to V kappa minus kappa ln P dash, I am writing E is equal to E kappa minus kappa ln P dash. This E kappa is same as corresponding to 1 unit pressure, that is 1 kilopascal, and instead of V kappa it is E kappa. So, E kappa is similar to V kappa in V ln P dash plot. Now, if you differentiate this, we will get dE is equal to minus kappa dP dash upon P dash, and the elastic volumetric strain increment, that is given as d epsilon P dash E. Please note that here the P dash corresponds to volumetric stress and E corresponds to elastic. The same thing we have seen, d epsilon P dash P means it corresponds to plastic. So, here it is elastic volumetric strain increment, you can write it as minus dE, that is change in void ratio upon original volume, that is 1 plus E naught. So, initial volume is 1 plus E naught, change in volume to its original volume, that is 1 plus E naught. That will give the elastic volumetric strain increment. So, we know what is dE from this expression. If you substitute this, you can get d epsilon P dash is equal to kappa by 1 plus E naught dP dash by P dash. So, this is what we get. But we also know d epsilon P dash E is equal to dP dash, that is stress by strain equal to K dash. Here it is volumetric stress upon strain, so it is bulk modulus K dash. So, d epsilon P dash E is equal to dP dash upon bulk modulus K dash. K dash is the bulk modulus. Now, substituting this, that dP dash by K dash can be substituted to kappa upon 1 plus E naught into dP dash. So, this and this gets cancelled off. One can write the expression for bulk modulus K dash is equal to 1 plus E naught P dash upon kappa. You can see that the bulk modulus can be determined by knowing the value of kappa and E naught and the value of P dash. Now, we already know the relationship E dash is equal to 3 K dash into 1 minus 2 mu. where mu is the Poisson's ratio. Substituting for k dash, we will get the value for E dash, that is 3 p dash 1 plus E naught 1 minus 2 mu upon kappa. And G, we know it is E dash upon 2 into 1 plus mu. Substituting in the value of E dash, we know that it is 3 p dash 1 plus E naught 1 minus 2 mu 2 kappa into 1 plus mu, which can be written as 1.5 p dash 1 plus E naught 1 minus 2 mu kappa 1 plus mu. So, elastic constants we can see whatever we have discussed here, it is all proportional to p dash. You can see in the expression k dash, E dash, and for G it is a function of p dash. So, elastic constants are proportional to p dash. This indicates the nonlinear elastic behavior. So, it is not that we simply substitute and get the result, it should be in an incremental manner. The computation of stiffness should be done incrementally. For OC samples, the elastic stiffness can be determined from isotropic consolidation, because we know it would follow the loading unloading line. And why should we have the elastic modulus for normally consolidated? Because that is going to exhibit elastoplastic behavior. When we say elastic response, we know that it is mostly relevant for OC samples. So, it was noted that estimating elastic constants from in situ stress states, it gives low values. That means, whatever we determine based on the in situ stress state will give low values of elastic constants. So, according to Randolph in 1979, he suggested that G should be determined from the maximum value of k dash. Now, what is meant by maximum value of k dash? Maximum value of k dash means it should correspond to maximum p dash. And what is the maximum p dash? That is the yield stress for that particular yield curve, that is the extreme point of the yield curve, which is p dash y. So, k dash max should be 1 plus E y p dash y upon kappa. So, that is according to the recommendation given by Randolph and others. So, this p dash y it is referring to, and the corresponding void ratio is E y, and G is taken as 0.5 of k dash max according to the suggestion. So, this is reported in this particular paper, which is driven piles in clay, the effects of installations and subsequent consolidation, published in Geotechnique. Okay. So, one can refer to this for further reading. Now, variation of soil stiffness with strain level, we can note that for a nonlinear material like soil, stiffness is a function of strain, it keeps changing. So, at a low strain, we know it is a linear response, and then it becomes a nonlinear response. Now, increase in shear strain decreases G and E dash. K dash decrease with increase in volumetric strain, because each of this is associated with shear response and volumetric change. So, there is a net decrease in soil stiffness with increasing strain. The response is divided into 3 zones based on the level of shear strain, which is given as how G, K dash, E dash varies with shear strain or volumetric strain or deviatoric strain. So, how does it vary? So, it varies something like this, is an S-shaped curve. There are some indications of the values, which is 0.001 percentage, 1 percentage. So, the strain which is less than 0.001 is considered as small strain, 0.001 to 1 percentage is intermediate strain, and greater than 1 is large strain. So, you can see that even a very small percentage of strain itself is considered as a large strain. In general discussion, it is considered like that. At small strain, stiffness is constant and soil behaves like linear elastic. So, here this is a linear elastic case where the response is stiff and we have very less volume change. So, or whatever is the amount of strain that is happening is quite less. and hence it remains more or less constant. At intermediate strain, stiffness reduces, soil behaves like elastoplastic, and there is a significant reduction that happens. At large strain, stiffness again becomes a constant value as the soil approaches the critical state. So, as it reaches critical state, then you can see that it reaches more or less the constant value again. For soil in the field, shear strain distribution will be non-uniform with higher value close to loading. So, when some loading happens in the field, what we can see that the strain will be high close to the loading location, and hence whatever is the stiffness in that particular zone, that drastically reduces as per the given discussion. So, as the strain level increases, the stiffness starts reducing. So, closer to the loaded points, you can see that the stiffness will be less as compared to other part of the soil, and that is how the failure zones or the failure points starts generating from a given zone. So, soil stiffness will be low in the loaded zone, and hence the failures are initiated. So, that is all about prediction based on Mccm. Let us summarize today's lecture. Prediction of failure of NC, LOC and HOC for CD and CU test discussed with respect to Mccm. For LOC, when ESP move beyond the yield surface, that is in QP dash plot, it results in deviating from the unloading line. So, we have shown that relationship with respect to yielding and the yield curve. So, from unloading reloading line, it deviates towards the critical state line, and that information we get because we have integrated yield curve along with ESP. After yielding, U in CU test increases non-linearly. If the slope of ESP is less than m, such an ESP will not meet critical state line and it will not cause failure. LOC soil can shear similar to HOC for cases such as excavation. Determination of soil stiffness is determined based on Mccm. According to Mccm, elastic constants are proportional to P dash. Computation of stiffness should be done incrementally. Even though there is an equation, it does not mean that it gives a particular constant value. For the range of P dash, it will be different. Variation of soil stiffness with strain level discussed. At small strain and large strain, the stiffness approaches a constant value. At intermediate strain, stiffness reduces drastically. So, that is all for this lecture. In the next lecture, we will see prediction of strains from the critical state concept. Okay. So, that is all for today. Thank you.